Let's now continue with another example. In this example, the matrix is a 3 by 3 matrix, and we are asked to find a basis for an Argon space for lambda equals to 2, an eigenvector. An eigenvalue. So we have some new words, basis and Argon space. So what does that mean? In this example, it shows that we actually can find multiple eigenvectors for a single eigenvalue, and that's very interesting. So it means that the Argon space dimension, the number of vectors that spans the space, is greater than 1. In the previous examples, we saw that for every eigenvalue, we only found one eigenvector. We found a basis for the eigenvector. Any scalar version of that eigenvector is the same eigenvector for the eigenvalue. But now we can see that actually for this matrix A with lambda equals to 2, there are two eigenvectors, or should I say two independent eigenvectors for this eigenvalue. So let's proceed. Right, so what do? We begin with always with A minus lambda I x equals to 0. We are given lambda equals to 2, so we substitute that over here. And now A is a 3 by 3 matrix, so I must be a 3 by 3 matrix. So this I is a 3 by 3 matrix. And we write A here. We write 2 times I here. So we have A here and 2 times I here. And now we have A minus 2I. Once we have A minus 2I, we are trying to solve for this equation of x such that x is a non-zero eigenvector. Okay, so how do we solve? Again, we perform row reduction on this matrix A minus 2I. Here the word augmented matrix because we padded the right hand side with the 0 vector. Alright, so let's proceed on, and we perform row reduction. We skip all the steps, and we found that we have one pivot and 2 free variables. In fact, this could have been observed here as well. You can see that this matrix definitely has only one independent column. The other two are nothing but scaled version of this column. Okay, so with that, we know that this matrix is singular, and this matrix has only one pivot because it has only one independent column. Alright, so once we can reach here, we want to find the general solution for x, which is we can write down as 2x1 minus x2 plus 6x3 is equals to 0. So this is a pivot, so we can put a square here, put a circle here for the free variable, and now we can solve. And remember that the free variable, when we say that they are free, means they can take in any values that we can assign to it. The pivots must be fixed, so typically we fix it as value 1. Alright, so let's proceed. So we have 2x1 minus x2 equals to 0 because we have assigned x3 to be 0 first. Therefore, 2x1 equals to x2 and x1 equals to half of x2. So we now assign x2 to be 1 because it's free, and therefore x1 will be half. So we have now a solution. x1, x2, x3 will be equals to half, and then x2 will be 1 and x3 will be 0. And in fact, we multiply by x2 because x2 can still be any value. And now we plus the second solution, which is, again, we have 2x1, and now we assign 0 to x2 and plus 6x3 equals to 0. And now we solve 2x1 equals to minus 6x3, and therefore x1 equals to minus 3x3. So again, typically we let x3 equals to 1, so therefore x1 equals to minus 3 times 1 equals to minus 3. And now we can write plus x3 equals to minus 3, x2 was set to 0, and x3 was set to 1. So this is the general solution for the eigenvector. So we now can proceed to see this here. So if you compare this to our previous example, you realize that for eigenvalue of equals to 2, the eigenvector has two independent vectors, and it is two independent vectors multiplied by its linear combination, so we call this the Argon space, and these two vectors are the basis for the Argon space. So these are all the terms you need to know. So we can write the basis as a set of these two vectors here. Notice that this lay changed the notation from half 1, 0 to 1 to 0. I mean, any scaled version of the original vector is also a valid vector for that basis. These two are independent, so a linear combination forms a space. So that blue shaded line is that space that we are talking about. Okay, now any vector on this space, and let's write it as 4 of them. Let's call this 1, 2, 3, 4. 1, 2, 3, 4, 4 points, and then multiply by a multiplied by any of these 4 vectors will result in these 4 vectors, 1, 2, 3, 4. Basically, these 4 vectors will be stretched by 2, the given eigenvalue. Its length will be stretched by 2. Its direction remains exactly the same. So this was the original 1, this was the original 2, this was the original 3, and so forth. Original 4. It doubles the length. Okay? So that's the key idea of this example. Now, if you want to have a sanity check, so typically we'll ask you to use MATLAB or Python to solve for the eigenvalue eigenvector. So in MATLAB it's easy. This is a syntax: A equals to square bracket the values of the elements of this matrix, and then to get new columns, get new rows, you put a semicolon. The EIG is the command for eigenvalue eigenvector decomposition. So EIG of A will give you 2 matrices. P is the matrix of columns of eigenvectors, and D is the diagonal matrix of eigenvalues. So we have A here, and we have P here, and we have D here. So we see that 9 is an eigenvalue, and 2 is repeated twice. And what about the eigenvectors? So this is V1, this is V2, this is V3. Okay, and then if you compare V2 and V3 to this guy, they don't look the same. But if you so why are they not the same? They are actually remember eigenvectors can be anywhere along this blue plane. Okay, so if you check carefully, these 2 vectors are definitely on this blue plane. And then why are all these funny numbers? Because the norm of this vector is 1. Okay, so MATLAB gives you a normalized eigenvectors. Okay, what else? Now, for description of the MATLAB's eigenvalue eigenvectors, please read it up. Alright, and one thing to note is that the eigenvalues produced by MATLAB is typically not sorted. So in this previous example, it was just an accident that it was sorted. Okay. Finally, you can go through the sanity check always for all our computations so that you can see that it is correct. Lastly, to summarize, in these few slides, what we did was to define what is eigenvalue and eigenvectors, And we saw that to find the eigenvectors, we have to exercise it in two steps. We first find the eigenvalues, and then find the eigenvectors by Gaussian elimination to solve this equation. Okay, you can see some more examples in these two slides. It will take you a while to get familiar with it, but typically after some examples you'll be okay. And in our quizzes and our tutorials, we typically restrict to 2 by 2 or 3 by 3 matrices. Alright, that's it for the 8.1 slide. Thank you.